Hello friends, today we are going to start with your new chapter, that is dual nature of matter and radiation. In this chapter we are going to start with the process of electron emission. We are going to study about it. See, what do we mean by electron emission? Suppose this writing board, this is a metal plate, okay. Now we have already studied it in chapter number 2, that is current electricity, that there are free electrons present in the metals. So we want that these free electrons should come out of this metal by any process. That process is called electron emission, the process by which electrons are emitted out of a metal surface. Now this is for sure that electrons won't come out of the metal surface on their own, because they do not possess that kind of energy. So in order to get the electrons out of the metal surface, we have to induce some process which are listed here. The first one is Thermionic emission. In some books you would often find it as Thermionic emission. Second one is field emission, and third one is photoelectric emission. I'll explain them one by one. For instance, the first process is Thermionic emission. In this process what we do is we heat the metal plate. So with the heat energy, these electrons capture that heat energy and they are now having enough amount of energy that they can come out of the metal surface. So that is Thermionic emission. Second one is field emission. In field emission, we induce a very strong electric field across this metal plate. For instance, suppose this side consists the positive and this side consists the negative side of an electric field. So electric lines of force would be going like this, from positive towards negative, penetrating this metal surface. Now while doing that, the strong electric field provides a strong potential to electrons, and that potential will give what? Potential energy to electrons. Capturing that energy, they'll come out of the metal surface, which is called field emission. Now these two topics are not included in detail in the board syllabus. So this photoelectric emission is discussed in detail in our syllabus. Now what is photoelectric emission? Supposedly light. What is light? Light is a form of energy. And how does light travel? We already know that if we have a source, then it will emit photons. What are photons? Photons are packets of energy. And how much energy each photons carry? And photons carry the packet of energy h nu. H is the Planck's constant, nu is the frequency of light. Now this packet of energy which is carried by these particles called photons, within this topic let me ask you a question. These photons, are they particles or are they waves? Like, do they possess particle nature or they possess wave nature? You should be able to answer this question correctly, because we have done this study in wave optics that photons or light, they have dual nature. Right, we have particle as well as wave property. Okay. Now these packets of energy, they are coming from the source on this. I told you that consider, suppose this is a metal sheet. So these particles of energy, they are coming and they are incident on the metal surface. Now what will happen to that packet of energy? We have metal surface wherein there are a lot of free electrons, right? So these packets of energy will come and interact with the free electron. This energy will be gained by electron and the electron will come out of the metal surface. This is called photoelectric emission. We are going to study this in detail. So now, in photoelectric emission, as I already discussed, friends, I have drawn a metal surface. Now if you are thinking about that metal surface is too thick, then let me tell you one thing. In molecular terms, compare the size of electrons and other atoms with the size of surface of metal. So the surface of metal itself would be really thick as compared to the size of electron. So that is why those particles which are present even on the surface can be shown like this. Okay. So this is a metal surface. It is not a thick metal sheet. This is a just surface. Okay. Now we have a packet of energy incoming called h nu. Okay. Now when this particle strikes an electron, this interaction takes place in two different ways. First way is this energy might be sufficient enough to push this electron out of the metal surface, completely out. This thing is called work function. So I'll repeat, what is work function? Work function is the minimum amount of energy required by this electron to come out of the metal surface. And then our electron has reached this point. What will it do now? It will travel, because now it was already a free electron, but it has now already come out of the metal surface. So it can move anywhere. But in order to do that, it must have, or it must possess some kinetic energy. And where will that kinetic energy come from? It will come from some portion of this only. So it will travel with the kinetic energy conditions applied. Now what is condition applied here? I'll tell you. What if the incoming incident ray or the photon or the source of light doesn't have that much energy, which is not sufficient enough to push this electron out of the metal surface? So in that case, there will be no photoelectric emission taking place at all. So we have termed this thing with a statement that yes, photoelectric emission can take place from all the metals. Condition applies, it all should have THREASHOLD, threshold frequency. Threshold frequency is the minimum frequency which this light ray or the light source must have, so that it can provide minimum bare energy for electron which is required to push it out of the metal surface, right? So if threshold frequency is there, electrons are definitely coming out of the metal surface, they are free, but they won't be able to travel anywhere. In order to this, for these electrons to travel anywhere, they must have some kinetic energy, and that kinetic energy will come only if this energy is greater than the work function. So this entire energy h nu is bifurcated into two parts. First part is the work function, which is the energy required to come out of the metal surface, and if there is any energy whatsoever left, that will be utilized in traveling. This is the major equation in this chapter, and we are going to study this equation again and again with different ways. We are going to change work function and kinetic energy in coming session. So this is the basic of photoelectric emission. So before we go into any further detail of photoelectric emission, let me tell you, Halbach and Lenard, these were the two scientists who first observed by some small experiment, I'll show you what, that photoelectric emission exists. What they did, they used a Goldleaf Electroscope. Now you are all aware of what a Goldleaf Electroscope does. If you are not, I'll explain. It's a small jar, vacuumized, with a metal rod and two leaves of gold. Now why particularly we use gold here? Because gold leaf can be beaten to very thin strips. These strips or leaf of gold were so thin that they were almost transparent, almost. Okay. Now how they used it, the gold, okay, I'll draw the leaf something like this, that these are not two lines, these are gold strips. Okay. So how they did this experiment was very interesting. They used a metal surface and they bombarded it with high frequency light. What they expected out of this experiment was, when this high frequency light will be incident on this metal plate, the electrons, free electrons, are going to capture the energy of incoming photons and they will get liberated out of the metal surface. This is what they expected, and when this will happen, since the negative charge has left the plate, so it is leaving the plate with all the positive charge. The plate with all the positive charge is now connected here with these two gold leaves. This gold leaf also will acquire the same positive charge, and what will happen if they both have positive charge? They will repel each other, right? This is what they expected and this is what happened. So this was the observation of Halbach and Lenard, that photoelectric emission is true and it happens. So following this experiment, Lenard and Millikan performed a detailed experiment on photoelectric emission. Now to study in detail about photoelectric emission, Millikan and Lenard devised an experiment. What they did, they took a vacuumized glass tube. This glass tube had an opening for incident light to come in. Then it consisted of metal plate A and metal plate B. Okay? An ammeter here, microammeter, to observe if there is any flow of current, and this setup was connected with the voltage source, which is like this. Okay, this voltage source was termed in a special way called potential divider arrangement. Now what is this potential divider arrangement? I'll brief you through it. Right now I have connected the negative terminal with this plate and positive terminal with this plate. The benefit of doing this would be, if an electron comes out of this metal plate, it will further be pushed by the negative polarity of the plate and it will travel easily towards positive plate, because the positive polarity would further attract the electron, right? So it would make the process easier. But if I want to stop the process, I could change the polarity of the plates by changing here, that is why it is called potential divider arrangement. Then what will happen? This plate will become negative and that plate would become positive. Okay. Now the process, the setup is simple, because these people, they wanted to know, they knew that photoelectric emission exists, but they wanted to know what are the further implications of photoelectric emission, or what are the things on which this photoelectric emission depends upon, like intensity of the incident ray, incident beam, frequency, what else. So that is why this experiment was devised. Now when this experiment started with incident radiation which was falling on the plate, that helped electrons to escape this plate and enter this plate. So that is how the connection between these two plates were made. As I already explained that this whole tube was vacuumized, so there was no other way that electron could travel from this plate to this place unless this action was supported by photons, right? Now the presence of current in ammeter showed that photoelectric emission is existing. Then the terms were changed. For example, the current flowing in this circuit was called as photoelectric current instead of current. The electrons flowing from this plate to this plate were called photoelectrons instead of electrons, right? Okay, so the first observation which was made was about intensity of light. So what do we mean by intensity of light? I'll explain. Right now, suppose there are two bulbs which are active in this room, which is falling on me on this board. Now if I increase that number of bulbs from 2 to 4, what will happen? Double light would fall on me and on this board. You won't see any more brightness, because brightness would change. Yes, it will change minutely, but the number of photons which are falling on this board and on me will get doubled. So intensity is what? The number of photons falling per unit area. That is what intensity is. And they wanted to know what is the effect of intensity on the photoelectric emission. So what they observed was, if I draw a graph between photoelectric current and intensity, the observation was something like this, that intensity is directly proportional to photoelectric current. And it makes sense. Why? Because what do we mean by intensity? Number of photons falling per unit area. If we increase the intensity, what will happen? More photons are falling on the metal plate. That means there will be more electrons which are now interacting with the photons, and hence there will be more electrons coming out of the metal surface. The process is very simple. And in books also it has been written like this, that intensity is directly proportional to photoelectric current, but I think there should be an asterisk sign here. That means conditions apply. And what is the condition? Yes, very good. We have already explained the condition, that the incident beam must possess what? The threshold frequency, because below threshold frequency nothing would happen. So above threshold frequency, intensity is directly proportional to photoelectric current. Done? Okay, let's move on to further point which is very important, the effect of potential. Now what do we mean by effect of potential? The potential voltage we have applied here. So should it make any difference if I increase or decrease the voltage? See, if it would have been a simple circuit then following Ohm's law, if you increase the voltage, then current would have definitely increased. But here, this current is not at all caused by this potential divider arrangement voltage. No, it is not, because the electrons emitted from the plates completely and whole solely depends upon incident radiation. So it is only and only these particles h nu, the energy packets, these are responsible for flow of current. So potential is independent of photoelectric current, or you can say photoelectric current is independent of electric potential. So that means even if the voltage is 0, there must be some current. Yes, and that is how the graph is like this. Okay, so students, one thing here, if I have to draw two graphs, I'll make it like this. Now you can see that I have increased the value of current. I'm showing photoelectric current on this side. I have increased the value of current by very small bit in both of these graphs. There is a reason. The reason is that supposedly, remember the first diagram which I made about the surface where there were so many free electrons entirely distributed, and then photons are incoming and these electrons are coming out, right? For some of the electrons which lie at the bottom of the surface, the energy given by these photoelectrons is not sufficient enough to make them go out of the metal surface and travel. So what is the least thing they could do is, these electrons can at least come out of the metal surface by utilizing entire energy, and when that happens, this energy is no longer sufficient enough to make them travel. So where is the rest of the energy coming from? That energy will come from the next h nu, right? But for these electrons, where are they right now? They are lying exactly on the almost outer part of the metal surface. So if you increase this voltage, these electrons are getting further assistance to travel towards the positive terminal of the battery or towards the positive plate. That is why I have shown a very minute, a very small amount of increase in the value of photoelectric current when I am increasing the value of potential. Done? This part is clear. Now I want to make this process stop. How can I do that? I have just told you that the potential divider arrangement is the easiest thing to do that. What I'll do is, I'll change the polarity. I'll make this plate negative, I'll make that plate positive. What will happen now? The electron which has just emerged out of the metal surface using this energy will get attracted back towards the positive polarity. True? But even if it has a lot of energy, it will anyhow manage to come up till this plate, but reaching here, it will further be resisted or further be opposed by the negative polarity of this plate, and that is how I suppose that this entire process is going to stop. But these scientists were wrong in predicting that photoelectric emission is going to stop immediately, because what happened was, for a minute electron, this packet of energy is a huge thing. So this packet of energy was sufficient enough to make the electrons travel even if we reverse the potential. So what happened? They reversed the potential. That is why I have shown a negative V side of the graph, and we were expecting that the graph should go immediately drop like this, but that did not happen. What happened was, they gradually decreased its value and ultimately at a point it came down to 0. So that means when you are reversing the potential, you will have to increase its value up to the point where the entire photoelectric emission from the plate stops, and that voltage is called stopping potential. So here I am marking it as V0. This is the stopping potential for this particular surface, and this is the stopping potential for this particular surface, right? Let us call them V01 and V02. Okay, so I have cleared. In brief, let us recapitulate entire thing. First of all, photons incoming having a packet of energy called h nu. They are illuminating a surface of metal having free electrons. These free electrons are getting that energy, are coming out of the surface. This emission is called photoelectronic emission. Traveling electrons, photoelectrons, the current taking place in this circuit is photoelectric current, and that photoelectric current is directly proportional to the value of intensity, provided they have minimum threshold frequency with them. And the next part, photoelectric current is independent of voltage, and yes, photoelectric emission is going to stop at a particular value of opposite voltage called stopping potential. I have briefed entire photoelectric emission in nutshell, but I would include a very important point here, which is, I have drawn two diagrams here, two different graphs I am having. Let us say one represents I1 nu 1, another represents I2 nu 2. What are these now? These are the intensities I1 and I2. Let us stick to this portion only, then I'll go toward that portion. Okay. Now I1 and I2 are two different intensity. So that means I2 must be greater than I1 because the value of photoelectric current is greater than for I2. And I have already seen that photoelectric current is directly proportional to intensity. That means higher the value of intensity, higher the value of photoelectric current. Hence the higher graph corresponds to higher intensity. So this fact is clear now. What about frequency 2 and frequency 1? I am coming to this point again with an indirect method. This is my graph for a particular source of light having intensity I and frequency nu. Okay. We know that intensity gets what? Intensity gets us more number of electrons which are coming out of the metal surface. But what is this frequency doing up here? Frequency is giving them enough energy to travel. That energy was opposed by stopping potential. True? So for one particular frequency, I can only have one particular stopping potential. Correct? Here I have shown two different frequencies. That means these two frequencies are giving different values of frequency. What? Different values of energy. Higher the value of frequency, higher will be the value of energy possessed by these electrons, and higher will be the value of stopping potential which is required to stop them out. So here with which we can say that nu 2 is definitely greater than nu 1 because it had higher value of stopping potential. Alright, let's move on to some equations. So with these observations, now we are able to sum up the laws of photoelectric emission. The laws of photoelectric emission are no new facts. These are the old facts which we have just studied. We are just summing it up in terms of laws. First one is, for any metal, there exists a minimum frequency called threshold frequency, below which there will be no photoelectric emission, right? Then above threshold frequency, photoelectric current is directly proportional to intensity. That was this one. Then the photoelectric current is independent of forward potential, which is this one. And lastly, the photoelectric emission is an instantaneous process. Instantaneous means the moment photons strike the metal surface, that moment the electrons comes out. Now, before I move on to further equations and graph related to this topic, I would like to bring down another topic coming out of this, which is the failure of wave theory. So what is the failure of wave theory with respect to the photoelectric emission? See, first point is, according to, okay, I'll write it down so that you can make your notes. We are doing failure of wave theory. Now we know that we were following two different theories when we were studying optics, the ray theory, the particle theory, as well as the wave theory, and that is why the topic, the heading of this chapter is dual nature. But wave theory failed in explaining few points. The first point was that according to wave theory, any frequency is suitable enough or sustainable enough to make electrons come out of the metal surface. But with experiments, we saw that there exists a minimum frequency called threshold frequency, below which this photoelectric emission would not take place. This was not described, this was not being able to explain by wave theory. The second point was, according to wave theory, light travels in the form of wavefront. Now, when this wavefront strike a metal plate, what will happen? This wavefront form a layer of energy which is evenly distributed everywhere. We have done this in detail in optics. So when wavefront interacts with the metal surface, suppose this is your metal surface. So this whole plane wavefront, when it is interacting with the metal surface, these electrons which are taking the energy down would require some time to absorb that energy and then start moving and then coming out of the metal surface. So according to wave theory, what should have happened? That electron should have come out, but after some time. But with the experiment, we saw that photoelectric current or photoelectric emission is an instantaneous process. So that means here the wave theory completely failed. Another point where wave theory failed to explain the fact that according to wave theory, light travels in the form of wave which has a certain amplitude. So no matter what, any amplitude should be suitable enough to get or to eject electrons out of the metal surface. But again, here also wave theory failed, because we have seen that intensity, with the increase in intensity we saw an increase in photoelectric current, but not with the increase in amplitude. So these are 3 points where you can see the failure of wave theory. So let's move on to the equations what we have studied till now. First of all, h nu, the packet of energy of incident photon, it got bifurcated into 2 parts, which was the work function and kinetic energy. So friends, we can change this equation. See how. For work function, we do know that the photon must have that minimum threshold frequency below which the photoelectric emission is not going to take place, and that is why W naught can also be written as h nu naught, where nu naught is the threshold frequency. For kinetic energy, we know that those particles which were traveling towards the positive terminal, right, they were doing what? They were getting repelled when using potential divider arrangement. When we change the polarity of the plates, that kinetic energy was opposed by the stopping potential, that reverse potential, and that is why kinetic energy can also be mentioned as EV naught. So with these 2 new terms, we have got a new equation which is h nu is equal to h nu naught plus EV naught. You can also write this equation in any form as you like it. For example, instead of writing like this, I can rewrite this equation as h nu, the above equation, is equal to W naught plus half mv square. Yes, I can do that because that's kinetic energy. It's my way of writing it. So all these equations are correct, but the most important one is this one, which is the h nu is equal to h nu naught plus EV naught, because this gives you a direct relation between stopping potential and incoming frequency radiation. Now, this is an important question which we are going to do right now. Is the question will be stated as this: give and draw a relationship between stopping potential and incoming frequency. I am changing the terms now. I can ask you, give a relation between frequency and stopping potential. See, both the sentences were different and our answers will be different. For example, if I have to, okay, I am dividing this board into 2 parts. Here I want to draw the relationship between frequency and stopping potential. Do try to keep a track of what I am saying and what I am writing, because frequency and potential sometimes look similar, so you have to listen and see at the same time. Second one, I want to draw the relationship between stopping potential and frequency. So what is the difference between this and this? In this, if I'll be drawing a graph, I'll be mentioning frequency on the y-axis and stopping potential on the x-axis. Whereas in this way, if I'll be drawing between graph of stopping potential and frequency, I'll be mentioning stopping potential here and frequency on this axis, right? Now, how to draw these graphs, how to get equation out of the given one? For that, we'll be using the linear equation formula for straight line, which is y is equal to mx plus c. You remember this formula? M was the slope of the line, c is the y-intercept. See, I will be converting this equation into this format for both this one and this one. See how. First of all, I want to do it for frequency and stopping potential. So I want to keep this frequency alone on one side so as it will do the job of y, right? So what I am writing is that h nu is equal to EV naught plus h nu naught. Okay, I am dividing it by h. So I'll get nu is equal to E over h nu naught plus h gets cancelled out, nu naught. I'll repeat, nu is equal to E upon h V naught, this is stopping potential, plus nu naught, this is threshold frequency. Now compare this equation with y is equal to mx plus c. Y axis we have frequency, the job is done here. On x axis we have stopping potential V naught, done. This is slope. Slope is positive. When I have a positive slope, that means the line will go in this way. Positive slope means it will make an angle, acute angle with the x axis, always, anywhere. Okay, so slope gives us an idea that line is going to go like that. If I would have got a negative slope, the lines would have come down like this, making an obtuse angle with the x-axis. This term being the most important, this is the y-intercept. Now y-intercept is positive. Positive means our line is intercepting y-axis at somewhere here. So this is how the graph would be. So this graph has these points where y-axis shows frequency, x-axis shows stopping potential, E over h, you can mention slope, m here is equal to E over h. Then the nu naught, which is the y-intercept, this is positive. Same thing if I do it for nu naught versus v naught versus nu. I was not saying nu naught, it was stopping potential versus frequency graph. So what were the changes? I want this equation, this term to be on one side. So I am changing it as EV naught is equal to h nu minus h nu naught first of all. Then I am dividing it by E. I will get V naught is equal to h upon E times nu minus h over E times nu naught. Okay. See, in this equation I am writing down the equation here. V naught is equal to h upon E nu, this is my slope, minus h nu naught over E. This is my y-intercept. So see, first of all, V naught, this is doing the job of y mx plus c. So y-axis has stopping potential, then comes x-axis, frequency is in x-axis, then slope. Slope is positive. Positive means the line is going to go like this, positive slope. So this is also clear that our line will go somewhere here. But y-intercept, this portion is negative. Negative means our line is going to cross the y-axis on the negative side. So the graph will go something like this. This negative y-intercept is minus h nu naught over E, and then the slope you can mention is h over E. So this is how any two given values can be given to you, or any two values can be given to you to make equations like this and then their corresponding graph. And hence the question will be framed as draw a graph between, let us say, work function and frequency. So you can make the graphs using the same method, using the equation y equal to mx plus c. So now let's move further and discuss about duality of the radiations. Now this is well explained by de Broglie waves. What we know about matter and radiation, that they have dual nature, but who established this? The establishment was initially done by de Broglie. See how? De Broglie said that the energy, what are de Broglie waves? I'll give you a brief note on that, that these are the waves associated with particles which are in motion. The point particles should be in motion. I'll explain you this point again, but first let's see that energy of a particle is given by the term h nu, which this we have been studying. Also we have known from Einstein's equation that E is equal to mc square, correct? Okay. So if I equate these energy, h nu is equal to mc square, what will I get? Nu can be written as c upon lambda. Speed of light was what? C is equal to nu lambda. So nu is equal to c over lambda. Mc square, c cancels out. I get lambda here, mc there. So lambda is equal to h upon mc. This is the wavelength of the radiation. But if I want to talk about the same thing for any other particle which is moving with velocity v, I'll get this equation as lambda is equal to h upon mv. This is de Broglie wavelength. Okay. Now two important things here is, first of all, number one, that here lambda is inversely proportional to momentum of the body, mv. That means for a particle having what? Zero velocity, zero momentum, it will be infinite wavelength, right? So that is why the Broglie waves are associated with only and only particles which are in motion. Second point is that these particles, these wavelengths are charge independent. No matter what the charge on the body is, the lambda is still going out to be same, and hence these are called matter waves as well, right? Let us take the same example. Let's take the same equation, lambda is equal to h upon p, and try to find out the de Broglie wavelength of an electron. Here momentum p, this formula is replaced by under root 2 mk. Where does this come from? See, half mv square is energy, okay, which energy? Kinetic energy. So if I multiply this term in numerator and denominator by m, I'll get m square v square divided by m. So we have got p square upon 2m is equal to k. So p square is equal to 2mk, and hence p is equal to under root 2mk. So this portion you don't have to see. P is equal to under root 2mk, and also for kinetic energy we replace it by electron volt EV, charge times the potential value. So k, instead of k we are writing EV. So the entire formula for the wavelength is h upon under root 2m EV. Now if you put the values of mass, charge and Planck's constant here, you will find that wavelength associated with electron is 12.3 upon under root v Armstrong. So here if I am accelerating the electron with any particular voltage, for example 10 volt, I can put the value of 10 here. If I am putting it, if I am accelerating the electron by 100 volts, I can put 100 here, and that is how we will find out the de Broglie wavelength of an electron. So moving further, Davison and Germer, this was the first experiment which clearly established that electrons have a dual nature. Okay, so what this experiment consisted of? First of all, we had an electron gun. This was a filament which was made to bombard or throw or eject electrons on a nickel crystal, where we have nickel crystal. Now this electron gun was maintained at some potential V, alright. Now these electrons, once they'll interfere with the nickel crystals, what they'll do, they'll get scattered at all the direction after reflection. So this scattering takes place almost at all the directions, right? So in order to see how these reflected electrons are like, they placed a detector D which was built to move in this path, and it was measuring two things. Number one, intensity of the incoming radiation, incoming electron rays, and number two, the angle at which it is coming. For instance, at this angle it was noting down some intensity of the incoming electrons, but this experiment started at some particular value of voltage. For example, let us say they started this experiment with 40 volts, then they increased the value to 41 volts, and detector took all the observations, then 42 volts, then again all the observations, and so on. So the observation was like, I'm making few graphs here. At this point, this side, I am marking down the voltage, 54 volt, this is 44 volt, this is 48 volt, this is 58 volt and 64 volt. These are few graphs. These graphs are marked with respect to their respective intensity of electrons as detected by this detector. What they saw was, there was a huge bump in intensity at 54 volt and 50 degrees. At 50 degrees and 54 volt, there was a huge bump as detected by the detector, whereas in rest of the cases, the bump was not as deep as it was seen at 54 volt. So the observation was, there were two conclusions. Number one, according to particle theory of light, according to particle theory, we just studied the de Broglie waves. So de Broglie wavelength was what? 12.3 upon under root V. For V, we have 54 volt here, this much Armstrong. So the value of wavelength came out to be 1.66 Armstrong. According to particle theory, this was the basic idea. But according to wave theory, the first order diffraction pattern, what they said was, these electrons which are coming, that these two electrons which are reflected by two very close nickel atoms. For example, what I'm doing here is I'm enlarging this diagram. So I have got two nickel crystal atoms. One electron got reflected from this one, second electron got reflected from this one, and now these electrons, as they have dual nature, they are traveling in the form of waves. Alright, now these waves are interfering, and that is why they are causing the bump. This was the idea behind the wave theory. So for wave theory, for first order diffraction pattern, they used Bragg's law, which is 2d sine theta is equal to n lambda. Here theta was 50 degree? No, it was not 50 degree. It was, if this angle is 50, this is theta and this is theta. So 2 theta plus 50 is equal to 180. That means 2 theta is equal to 180 minus 50 is 130 and theta is equal to 65 degree. So for nickel crystal, lambda was 2d sine what? Sine 65, and d is the distance between these two closely placed nickel crystal, where the interatomic separation for nickel crystal is 0.91 something Armstrong, and if you put all the values you get the wavelength to be 1.65 Armstrong. 1.65 Armstrong. So these two results were in huge coherence, and that is why it was established that electrons have dual nature. So with this topic we conclude the chapter. We'll meet again in our next chapter.